Okay, so I'm Izhar, and I'm going to talk to you about photonic quasiparticles and their strong coupling to other systems. So let's begin. So you all probably know what is a photon, right? So we have an electromagnetic field, and according to quantum field theory or quantum electrodynamics, we quantize it. So we take time harmonic modes, solutions of Maxwell equations, and these have a frequency of omega, and we normalize them to carry an energy of h bar omega. So these are our photonic modes of the system. Now, usually we think of this in the framework of a far field radiation, right? Plane waves in free space with no boundary conditions or anything. But as you know, electromagnetic fields can do all sorts of different weird things, and they have unique ways. So in these conditions, we generalize the notion of a photon to a photonic quasiparticle. So this is the general idea. We have some sort of material which has an electromagnetic response. It interacts with the electromagnetic fields, and we find for this material electromagnetic response functions. So we find a dielectric constant and susceptibility. We plug them into Maxwell's equations. We solve them, and the solutions that we get, the modes that we get, we normalize them, and we find the single photonic modes of the system. So here we have a lot of different examples of materials which have, or systems which have electromagnetic responses, and when we quantize them, they lead to a lot of different types of photonic quasiparticles, some of which you've heard of, and I'm going to talk about some of them. So the simplest example is a cavity photon, where we basically, the only thing that we change from far field radiation is just that we add boundary conditions. So the main interesting thing about this cavity photon is that because, as you know, energy density is proportional to the square of the field, so if we want to keep a normalized energy, so for a single photonic mode, we can make the volume smaller and make the fields larger and get larger fields. And when we have larger fields, we have higher interaction with other things. So this is why we are interested in these cavities. Now, as you know, thermal effects will destroy everything good in the world. So a photon in a cavity will decay in some time. And here we have, for example, a plot of electromagnetic field in some point. And as you can see, it oscillates, but it also decays. And then, as you can see, we have two examples. This blue one decays more quickly compared to its frequency than the red one. So when we look at the Fourier transform of this, we have these shapes, which are actually Lorentzians. And you see that the one which decays more quickly has a higher bandwidth. So the lifetime of the photon in the cavity is related to its bandwidth, and we quantify this by the Q factor, which you already heard of, and this is the ratio of the frequency to the bandwidth. So the higher quality the cavity is, the higher the Q factor. So another example of a photonic quasiparticle is the surface plasmon polariton, where in this case, we have an interface between a metal and some sort of dielectric. In this example, it's like air. So what we have is some photon or something excites oscillations of the electrons in the surface of the metal. And these oscillations coupled with oscillations of the near field radiation on the surface of the metal. And this collective excitation is termed a surface plasmon polariton, where plasmon refers to the oscillation of the electrons, and polariton refers to the light mode, photonic mode of this near field radiation. And again, this radiation is highly confined, exponentially localized on the surface of the metal. So we have a higher confinement and thus higher electromagnetic fields, again, like the previous example. So let's talk about this interaction of photonic quasiparticles to other systems. So we are going to talk about discrete systems, so systems which have discrete energy levels. We call them quantum emitters because when they move between energy levels, we either absorb or emit a photon. So we can separate the interaction of our photonic quasiparticle with the system into two regimes. So in the weak coupling regime, the interaction is weak enough so that the quantum states of each system remain roughly the same. So we can treat this with perturbation theory, and the systems are not entangled significantly. But in the strong coupling regime, the system hybridizes significantly, and we'll talk later about what is the exact criterion for this. So in this state, perturbation theory no longer holds, and we have to resort to some other way of solving this interaction. So let's see how we can treat this interaction. So this is a very fundamental Hamiltonian in a light matter interaction, which is called the James-Cummings Hamiltonian. Basically, what we have here is an harmonic oscillator. You recognize this as the energy term. So we have an harmonic oscillator with levels, where each level signifies an occupation number of the photonic mode. Here we have a two-level system, which is the quantum emitter that we're interacting with. And this is the interaction term. So we have here two terms corresponding to either absorption or emission into the two-level system. And this factor here, this frequency, is the interaction strength. And for example, if you calculate this for an atom which you place in a cavity, an atom which can transition between energy levels, we get this factor where this is the dipole transition moment. And now the important thing to note here is that we get here the mode volume. So when the cavity is smaller, the interaction strength is higher. And this is exactly what we talked about earlier about the electromagnetic fields being higher when the cavity is smaller. So when we solve this Hamiltonian, for simplification, we assume resonance, but it is not necessary. We get the energy levels, which were previously degenerate, are now split by this term. So this is called Rabi splitting. And so here is an illustration of that. We have the two-level system, and we have our optical mode, which has N2, which jumps from an N equals 0 to an N equals 1 occupation number. And when they interact, they form two new energy states, which are separated by this Rabi frequency. And here we see a plot of this, where we have an empty cavity, which has a single resonance spectrum. But when we place an atom in this cavity, we find that the spectrum is split into two separate frequencies, which is exactly what we predicted from quantum mechanics. So now we can formulate the criteria for strong coupling more precisely. We say that we are in the strong coupling regime when this splitting between these two peaks is separable among the bandwidths. So if they are closer than the bandwidth, we can separate them, and we can experimentally prove that there is a strong coupling. So this is related to the lifetime, as we previously stated. So this is a beautiful example of Rabi splitting in a photonic mode. So what we have here is a gold nanoparticle, which we place in on a gold film. And you can see that on this plot, this nanocavity hosts a very highly confined electromagnetic mode, which is actually a surface plasmon polariton and the interface between film and the dielectric and the gold and the dielectric. So we can see that if we place here a fluorescent molecule, which is a quantum emitter, it can decay and emit light. If we orient the molecule to emit to that direction, it will emit to a far space photon, and we see a single resonance peak. But if we orient it to emitting to this confined mode, we see a split peaks, just like we predicted in the Rabi model. So this is another example of this same phenomena. We have here a photonic crystal, which has a cavity in it, and this cavity hosts a highly confined photonic mode. And if we place quantum dots, which we already learned have discrete energy levels, if we place them in this cavity, when we look at the resonance spectrum of this curve, we find a splitting in the energy levels. We saw how this Rabi splitting appears in many different systems, which this is a simple prediction of quantum mechanics, but we saw it in different systems of light matter interactions. And when we looked at these two systems with the generalized framework of photonic quasiparticle, we noticed this repeating phenomena of Rabi splitting. And of course, there are many other examples, which I don't have the time to talk to. And another point that I've also didn't expound on is that because photonic quasiparticles are highly tunable, we can engineer their systems to control many different properties and of the light matter interaction, and then we can create new technologies which are very important in the future of humanity. Okay, so thank you. Yes.
Can you return to the slide with the results of the fluorescent material?
Yeah.
What is the reason that the amplitude of the peaks is different in the different modes?
Well, this is because the the frequency of this molecule is not in resonance with the frequency of this confined mode. So we have other corrections to the Hamiltonian. We need to treat it more precisely. So yes.
Is it necessary to treat the photons as photons and not like classical electron and wave? I mean, is the in the Hamiltonian you showed it as photon, but if you take it as the classical wave,
Yeah, so precisely this rapid splitting is a quantum mechanical phenomena that stems from quantum mechanical Hamiltonian, and this is actually done for a single molecule, so which emits a single photon. So this is actually a purely quantum mechanical
but I
phenomena.
mean, you get the splitting of the energy levels of the two level system. You still treat it quantum mechanically, the two level system, but you take the laser, the light to be classical. So
yes, this is
like coupling and splitting of the energy levels, but you don't treat it with photon.
yeah. So this you are correct that we get rapid splitting when interacting with classical light, but if we do this for a single molecule, then this is a single photon, and we get the result of the James-Cummings Hamiltonian, and we can actually get more results on this that appear only on the quantum mechanical regime. Yes. Yeah, so the rapid splitting, as we get solved here for this simple case, we get that we can either increase the number of photons in the photonic mode. So the higher the intensity of the photonic mode, the higher the splitting is. But we can also increase the interaction strength. So if the interaction strength, which stems from the volume of the mode and other quantities, is high enough, then we can see this splitting even for a single photonic mode, which is what was demonstrated in this experiment, which is the single molecule. Okay. So thank you.
Thank you. Great time.